We have an example here. A 10 centimeter by 10 centimeter square loop lies in the XY plane. The magnetic field in this region of space is B equals 0.3 T I hat plus 0.5 T squared K hat. This is in Teslas, where lowercase t here is in seconds. So this is telling us the magnetic field value in this region of space is changing with time. So our question is, what is the EMF induced in the loop at the time t equals 0.5 seconds? So we have our coordinate system, x, y, z would come out of the screen. We're told that this square loop is in the xy plane. So it could be up in the first quadrant. It doesn't even actually have to be aligned with the x and y axis. What has to be the case is that the square itself, the whole square area, is in the xy plane. With that being the case, that means the area vector, the area would be each side squared. So if I called each side an L, which we know is 10 centimeters, the magnitude of this area would be L squared. The direction would be normal to that surface. So K hat coming out at us, or negative K hat would work as well. Having a positive versus negative flux doesn't mean a whole lot to us when we have just a two-dimensional surface right now. So regardless of how we align the sides of this square, this area vector is going to be the same thing. The area of the square is the two sides squared, so 10 centimeters by 10 centimeters. Normal to the surface is in the z direction. Okay, so they're telling us that there is a magnetic field in this region of space. This magnetic field has an x component, that's the I hat term. So has an x component and it has a z component. Both of these components are changing with time. So the value of the magnetic field is getting bigger and bigger as time goes on. The question wants us to figure out the EMF induced. When you see a problem involving induced voltage, induced current, a good rule of thumb is to jump to Faraday's law. Faraday's law is telling us there is an EMF induced when flux is changing with time or over time. And here's the number of loops or turns of coil in the problem. We have a square loop, so we would say that n equals 1 in this particular case. But to find this induced voltage, we need to have a function. We need to determine the magnetic flux through our loop as a function of time. If the flux is not changing with time, then there won't be any induced voltage. So let's come over here and think about flux. Our fundamental equation for magnetic flux is B dot dA. This magnetic field, if we think about one single moment in time, as if we could take a photograph somehow of the magnetic field. At any one given moment in time, if we look at our equation up here for B, we would find B is one specific value. That means the magnetic field in this case is uniform in the area. So, for example, at time equals 1 second, just to choose an easy value to put in, if I put in 1 second into this equation given in the problem, I get 0.3 I hat plus 0.5 k hat. At this exact moment in time, this is a constant. It's uniform. It means that everywhere in our square, so even if coming up to the squares I've drawn, a point closer to the origin, a point farther from the origin, both x or y, all these points will have the same value of b at t equals 1 second. Every single point, there will be an x component of the magnetic field and a z component of the magnetic field. The x component will be 0.3 Teslas at the moment of 1 second. The z component will be 0.5 Teslas at that same time. So it doesn't matter where in the area I'm talking about. So if I come to the first rectangle or square I drew, it doesn't matter what point in this square I'm talking about, the magnetic field strength will be the same in the x and z direction for every single point. This is what we mean by B, the magnetic field, being uniform in the area. When that's the case, we can say the magnetic flux is simply the magnetic field vector dotted with the area vector. We already know the area vector is 10 centimeters by 10 centimeters in the z direction. When we do the dot product, we're finding the components of the magnetic field that can actually pass through this square. Our magnetic field, we know, has an x component and a z component. The x component of the magnetic field, if I just draw a vector representing the x component, this does not pass through. Because of how the square is oriented. Only the z component can pass through. So doing the dot product, I don't know if you recall, we would take the x component of both vectors and multiply them together. I'll write that out. So the x component of the magnetic field times the x component of the area, the y component, just generically, this is how we would write out the dot product. We do have an x component of the magnetic field, but we do not have an x component of the area. The area vector is normal to the surface, meaning perpendicular to the surface. That's why we wrote it up here in terms of k hat. So we only have a z component, k hat, a z component of area. So our flux in this particular case will only be the z component of the magnetic field times this area vector that's only completely in the z direction. So coming back to my equation given in the problem, the z component of this magnetic field is 0.5 t squared. The area vector is just the two sides squared, the 10 centimeters by 10 centimeters. So this describes how our magnetic flux is changing with time. L's not changing. Our loop stays as a 10 centimeter by 10 centimeter square loop. But the time is going to be changing. This magnetic field is getting stronger and stronger as time goes on. So it is this equation for our magnetic flux that we need to come back and plug into Faraday's law to find the voltage. EMF. Number of loops in this case we already know is 1. The derivative of the magnetic flux with respect to time. So this equation we just came up with for flux, we need to take the derivative of that with respect to time. So we have the 0.5, that's a constant. The L squared is representing our 10 centimeters by 10 centimeters. That's not changing. It's this t squared term. The derivative of t squared is 2t. So we find that the derivative of the flux with respect to time is L squared, L being the 10 centimeters, and then we still have t in here. Writing out Faraday's law, we have one loop, so n equals 1. The derivative of our flux we have found, L is 0.1 meters. That needs to be squared. We still have t in here. And so this EMF is going to still be changing with time. So what we have right here is 0.01 t is the induced voltage. That's what this represents, is the induced voltage or EMF in the loop. Having a t in here is simply telling us that the value of this induced voltage is changing with time. That's also part of why they told us in the problem to find the EMF induced at the time of 0.5 seconds. So if I plug in that time, I find that the induced voltage is 0.005. This should be in volts because voltage, that's how we measure it, an EMF. Where these units are coming from, flux itself will have units of Teslas because of the magnetic field. I changed the 10 centimeters into meters. So Teslas times meters squared is the units of flux. And then dividing by time, when we take the derivative, that's when we're getting the per second aspect. This is where our volts are coming from, which I have a hard time remembering all these units. If you look in the test notes, right now, we have units on page 3 of our test notes. We're told in here on this page that a Tesla is a Newton per amp meter. We're also told that a volt is a joule per coulomb. We know a joule is a Newton times a meter. We know an amp is a coulomb per second. So let's make sense of what we have up here. if I have a Tesla times meter squared per second, newtons times seconds, so I'm plugging this in, over coulombs times meter. Let's see. Times the meter squared over seconds. So all I did was plug in T right here. This meter cancels with one of those. This second cancels with that second. So I have a Newton times a meter over a coulomb, which is a joule per coulomb, which is a volt. Now, I do not typically go through and make sure my units are exactly right every single time. I trust myself that if I'm accounting for everything in the equation and making sure that everything is in SI units, that my answer I get here will have the appropriate units. I do realize that may not always be the correct thing. I might make a mistake for sure, but as you can see, following the units through can be a bit of a challenge sometimes. But I did want you to see where it came from this first time. Okay, so note any problem. In general, if you are asked for induced EMF, induced voltage, or induced current, Faraday's law is likely going to need to be used. So you will need to write the flux in terms of time so that you can take the derivative of it to get to induced voltage. Okay, we'll do another example as well, and I'll do that in the next video.